probably if you're a grad student, you're probably thinking it's been a while since you've moved to Champaign. You tried to leave Champaign. That's what I always thought when I was here. Now I miss it. So as Dan said, I did my dissertation with Larry whenever I was here, and I remember so in the quant program, you eventually expected to present at the brown bags. And I remember my first presentation was either at the end of my first year or the very beginning of my second year. And at the time, Rod McDonald was one of the faculty members here. And I gave my presentation, and Larry's like, hey, look at this really cool cluster analysis problem. And I looked at it, and I was like, presented it. And then the first question that anybody ever asked me in my academic career was just Rod, was less of a question versus Rod just saying, I don't believe in clusters. And then he just left it at that, like waiting for a response. And I was like, I don't know what to say to Rod McDonald that he doesn't believe in clusters. Maybe he's right. And then afterward, Larry told me he didn't believe in factors. So I was like, well, where's that leave me? It's like, one guy doesn't believe in clusters and one guy doesn't believe in factors. So that's kind of what I'm going to try to talk about today, is like, how do we understand, do we have factors or do we have clusters? Or do we have a mixture of the two? And so I kind of talk, there'll be some equations, but mostly I'll just explain those away and kind of just talk about the process and give you maybe a few recommendations of what you should do from a practitioner point of view, but also just how you should maybe want to start thinking about some data. Right? So in terms of psychological data, there's this whole issue of determining how clusterable psychological data is. And it kind of there's a nice review paper by Meal in '95 that talks about this. And then one question really we're talking about is, are we constructing valid categories or groups from some kind of indicators, which are usually just variables that we have in psychological traits. And it's kind of been posited this is like essential to psychological sciences. And this kind of allows us to test whether these groups are actually different on this kind of underlying constructs and what's going on. And there's this big question, and then Meal kind of, in my opinion, went off on this tangent of this whole taxometric procedure things that you'll read a lot about, like how do we do this diagnosis. I won't talk a lot about that today. But there's also this addition that's like, well, if we have this underlying construct, should we think about it as a continuum? And is it some kind of, do people kind of move gently along the continuum? Usually, if you can think about like depression as a common example, maybe you kind of are not depressed, and then maybe a little bit depressed and more severely depressed, and then maybe diagnosably depressed. And so you can think about that almost any kind of clinical construct in psychology could be represented like that, where it goes from one end to the other. Or do you think about, do we have depressed people and not depressed people? Is it better to think about it as a categorical representation, right? And then some people say it doesn't matter that much. You can think about it either way. Who cares, right? Just think about it. That'd be a step in the right direction. And then there's other people that says that it really matters how you do the initial conceptualization, because that will influence how you build the theories that are based upon whether having a continuous representation or a categorical representation. And then Meal kind of advocated in '95 that he solved the problem, which I guess the fact that I'm here indicates maybe that wasn't the best the best thing to advocate. I don't think it's necessarily solved. So it's used a lot in psychology, and in specific example, as Dan mentioned, I do a lot of research with alcohol addiction. And so the alcohol addiction, there's been several proposed categories and subgroups throughout the years, starting back maybe the first one in the 30s, and then they just kind of differentiated it between a moderate drinker, a problem drinker, and a real alcoholic. So you can see in that case, you have the classes are actually lying on a continuum, where you have like, oh, you don't really drink that much, maybe you drink a little bit more, now you drink more, and now you drink now you have a lot of problems. And then throughout the years, there's been these whole kind of refinements of what types of alcoholics we have, what types of alcoholism there is, what does that mean for treatment plans, and so forth. So even though it seems at some level it's kind of arbitrary what we call these classifications, at the end of the day, in terms of a practical effect, there will be a different treatment plan for different types of alcoholics. Some of my research works on like how soon can we classify people into a specific treatment regimen, for instance, to get the best outcome measures. All right. So, but at the end of the day, very few researchers actually formally test their data for any kind of cluster structure that exists. It's still seen as a very exploratory analysis, and we don't look in terms of replicability, whether we can keep drawing out the same cluster structure. What happens is this causes kind of a rise and fall of different typologies that have existed throughout the years. And alcoholism just is one example. You could pick, definitely in psychology, you could pick any kind of psychopathology domain, and then this has probably existed where people have talked about types versus continuums, whether it's schizophrenia, depression, anxiety, just anything you can think of. Then what happens is you get in this you get into this area that's actually been a controversy over the last few years in psychology, is you're getting these results that are very difficult to replicate or maybe not replicated at all. So you have a paper published, they say, hey, there's these groups, then it gets cited a little bit, people talk about it, and then another paper can't validate it and says, no, I think there's these groups, and there's not really a consistent core message that goes out through psychology. So today I'm just going to kind of talk about, first I'll start off talking about the link between maybe factor analysis and a form of cluster analysis, which I'll call latent profile analysis, is just a kind of nod to the historical developments. But it's just also a specialized form of mixture modeling, if you're familiar with that from a statistics point of view. All right, so we'll talk about that, then talk about maybe some diagnostic approaches you can use in that context if you're analyzing real data to determine, do you really have a class structure? Should you think about this as a factor model or not? And then we'll move on to extracting subsets of clusters on the same data set where an individual might belong to several different clusters across several sets of variables. Instead of thinking, the big analogy I always think of is when I was a kid and watched the Bugs Bunny cartoons, there's this one cartoon I remember where like Bugs Bunny was like dressed up as a grandma, and like Yosemite Sam was like courting Bugs Bunny to like move off to the west, and so Bugs was packing up the house, and Yosemite Sam said, what are you gonna do, take everything in the kitchen sink? And then the kitchen sink like flies down and like lands on Yosemite Sam. It's the same thing I feel like a lot of times applied researchers do, where it's everything in the kitchen sink goes into the analysis. So there's no thought about like, do all the variables contribute to the same cluster structure, or do we just have these variables, so let's analyze them, right? And that's usually what I see happening a lot, whether that's a cluster analysis or whether that's a regression. It's like, hey, I'm gonna try to predict this, and here's my 20 predictors in my regression model. And so at some point it just becomes a little bit ridiculous. Right, so let's just talk, so latent profile analysis is just a statistical approach to extract groups based on some kind of underlying theoretical model. Right, so here what we have, the important things to take away from this is that we're gonna have K groups. So we'll just have K different groups, and each observation will have some probability to belonging to each of the different groups. Right, so if we have 3 groups, then maybe I have an 80% chance that I belong to group 1, a 10% chance to group 2, and a 10% chance to group 3. Right, so everybody has a probability of belonging to one group, and then all your probabilities add up to 1. So it's just like a way to decompose each person's observations across a set of groups that you're positing. Right, and this is just, all this is just saying is we're assuming some kind of local independence. So the variables, once I know the group structures, then the variables are uncorrelated. Right? So it's a nice way to decompose the data set into almost like a data set of additive properties once I take into account the group structures. So if I extract the group structures, then it simplifies the entire process. Right? So the entire goal of this is just to find these groups. And this is, so I call it latent profile analysis. It's, in psychology, it's just being more, and educational psychology, it's just being more generally termed as latent class analysis, versus latent class analysis used to refer to just whether you had binary data or not. But now it's kind of just a catch-all term for everything. Right, if you're in statistics, like I said, it's called finite mixture modeling. It's called something else if you're engineering. Right, so then we can talk about, well, it's the links between latent profile analysis and exploratory factor analysis. And the equations themselves aren't that important, besides the fact if you've ever had a factor, like if you're familiar with factor analysis, this is just our covariance matrix of our variables. So how are all our variables related? And that can be decomposed into 2 parts, where you have, here's how the variables are related to the underlying factor structure I'm trying to extract, and this is just basically the error term, or the uniqueness, or however, whatever flavor you learn. So this is the common thing that everybody learns in their multivariate statistics class or their covariance structure analysis class. This part usually is not taught within the course, but this is just saying I could rewrite the latent profile model like this, where it kind of has the same form. The only difference is A has 1 more column than lambda, right? But they both recreate the sigma matrix, the covariance matrix, to the same degree, right? So you either can have a representation with K classes or K minus 1 factors. So that means that any covariance matrix can be equally well represented by, for instance, a 1-factor solution or a 2-class solution, or an 8-factor solution and a 9-class solution, right? So at some level, in terms of if you're looking just towards how well am I estimating the covariance matrix, it truly is arbitrary whether you pick a continuous representation or a categorical representation. So you can't really live on model fit alone. Right, which is where I feel maybe like a path we've meandered down in terms of, I don't want to say like the over-influence of the field of statistics on the social sciences, but it's definitely like everything has become model-based, and you can test it with a likelihood, or here's my BIC or whatever. And model fit can't disentangle everything. Right? And then once we do our factor model, you could project your data down into the factor space, right? So your data kind of live in this whole full data world, to borrow a term from Larry when I first semester here. So they all live in the data world, and then after we get the factor model out, you project them down into the factor world, right? Through this relationship between the factor loadings that everybody always interprets. So you could have your data actually represented as factor scores, which is all this is, and this is kind of irrelevant just for completeness. So you have your factor score. So you go from your original data, then you go to your factor space, and right now we'll just assume we're doing regular out-of-the-box exploratory factor analysis. So everything can be uncorrelated. We're not going to do any rotations or anything like that because it's kind of arbitrary to the point being made. You can still do the rotations if you so wanted. So we go from our original data to uncorrelated factor scores, and we look at our factor scores, and that's where people usually go, like, just go wild with everything, right? You have your factor scores, you can put your factor scores into a regression model, you can predict things with your factor scores, you can you interpret your factor loadings and say, oh, look, these variables are very important for this factor, and this is what this means. And one of the key things to remember is, I guess, the kind of the most recommended practice right now is to do maximum likelihood estimation, and the only importance that has is that it makes sure that your factor scores, the only important relevance for this, it has a lot of other things, but the relevance is it makes sure your factor scores are normally distributed, right? So you're going to have this multivariate, either if you have one factor, it'll be normally distributed. If you have a lot of factors, it'll be multivariate normally distributed. So a very nice, clean distribution, right? And then if I were to look at the covariance matrix of the factor scores, I could decompose it like this. And what happens is if I have an infinite number of indicators per factor, then this part, the variance of the factor basically goes to 1 because I fix it to 1 when I extract it. So the covariance between the factor scores themselves will go to 0, right? So it just kind of disappears, right? So what happens if I have multiple classes, I'll get mass at each of the means of the classes. And you can see, and this is like, you're like, whatever. If we look at some distributions, we can see why this is important, right? So this is just fitting to some data, common factor model. This would be a standard 3-factor model to a data set that really has a class that does not have a class distribution. And there's not a lot of, it's a low number of observations, so I don't get the perfect normal curve, right? Versus if I actually have class structure in my original variables and then I fit a factor model to it, then if I were to look at the factor scores, plot the actual distributions of the factor scores, then you see a multimodal distribution within the factor scores, right? And each of these modes are centering around a different class mean. Right, so from a practical point of view, all you have to do when you do a factor analysis is, like, even if you do it in SPSS or something like that, just plot your factor scores, plot the distribution of factor scores. And if you see multimodality, then you probably don't really have a factor, the factor model is probably inappropriate. Right? So it's just a diagnostic procedure where you can just go the one extra step, which says plot factor scores, and you can see how appropriate it is. And as the sample size increases, it becomes much and much cleaner. Right? So if we increase it to 200 observations, then the dip between the modes get more. Like 800 observations, you start to pull out the third factor. You remember it's hard to pull out a mode for all the factors because since these are factor scores, they're constrained to be standard normal. So it's forcing to have a mean of 0 and a variance of 1. So you're trying to pull out multiple modes while still maintaining the variance of 1. Right? So you're trying to get the modal separation but still bounding the spread of the factor scores. So that's why it takes a lot of observations to see how many groups there are. So if you have a very large data set, then you can see, in this case we have 4 groups, you could see a factor score actually have the modes center on the number of groups. But that's with 10,000 observations. If you have a fewer number of observations, the number of modes doesn't have the power to converge to the number of groups. But if you saw something like this, so this would be if it had a class structure originally, this would be if it was really just a continuous underlying structure. Right, so if it's really a factor model, they look normal. They're supposed to look normal and they look normal. But if it's not really a factor structure, if it's a class structure, they don't look normal at all. Right, so this is just the first kind of diagnostic, what can I do in terms of making my factor analysis better? So you should look at, and it's just like, it almost feels like a silly thing to say because you should be saying the same thing like when you do regression. You should still be plotting your residuals and looking at your residuals and saying, hey, is the regression model appropriate? It's the same kind of thing. Is the factor model appropriate? And it either is or it isn't. In this case, it wouldn't be in the top, but it would be in the bottom. So it's just a nice, easy, simple check for something that also has like a mathematical underpinning of why that should be. And so that's kind of step 1 in disentangling whether we have continuous or latent spaces. Right? So if I want to, and then we can say, well, how well does this work? Is this like, you just saying something that never works? So we can test it if we want to. And we could do some kind of simulation approach, which is usually just kind of generate data from where we know the real structure and then test how well our decision point pulls out that structure. So in this case, the decision would be, do I observe multimodal factors or do I not observe multimodal factors? If I observe multimodal factors, then I'll say, oh, you came from latent profiles. And then if I observe normal factors, I'll classify you into this section. So I'll have an actual decision rule, and I want to just see how well the decision rule works. Like under what conditions it works, under what conditions it doesn't work. All right, so I can generate a lot of conditions. So here we just looked at what's usually done within the social sciences. And so anywhere from 2 to 6 groups is pretty common. It's pretty rare in the social sciences to see anybody extract more than 6 groups. I think 6 is kind of the general upper bound on the number of groups. And we looked at, and for the, just to kind of not bias it too much in the case of power, we just looked up to 200 observations. So kind of the lower threshold of when I could start expecting modes. And we also looked, instead of this perfect situation where all our variables come from normal data, we looked, what if we vary it and we have more realistic data, where we have some kind of skewed data, we have maybe mixed data where some variables are normal, some are skewed, things like that. And then we just, for our latent profiles, we just overlapped them. The overlap between the classes just means if you could imagine 2 clusters existing in space, so 0 probability of overlap would be like cluster 1 here and cluster 2 here, but like 30% overlap would be if you like imagine a Venn diagram moving together, and then the area within the sign, the whatever that's called, the overlapping circles. Right, and we can imagine different types of overlap, joint or marginal. Right, so joint, I think I have a picture of that to help it make. So this would be like a case of marginal overlap. So they only it means it only overlaps on the margins. So it's not really overlapping in the joint multivariate space. Right, so this should be easy for any kind of cluster or mixture modeling. And these are like some kind of normal data, but I drew boxes. I should have probably drawn ellipses or something like that. But at the time, it was easier for me to draw a box. And so path of least resistance resulted in boxes. Versus, which that excuse falls down because it's definitely not easier to draw like a pentagon than it is an ellipse. But this is the same kind of thing. This is classes that are beginning to overlap. In this case, we made them overlap on a single dimension. That way, if we were to bias, and after a lot of discussions with Rod, his argument always was, if you're going to make 2 mistakes, like one of 2 mistakes, what's the bigger mistake? And he would always argue that the less worse mistake is to think that classes are actually a dimension. And it's a bigger mistake to impose classes on a dimension, something's really a dimension, and claim that it's classes, because you're imposing an actual physical structure on something that doesn't have the physical structure. Right, so here we tried to bias it in terms of the factor model. Right, so this looks like if they become overlapping enough, then who's going to ever tell us a difference between just some kind of continuum that exists through here. Right, so as we move them closer together, we want to test how well this thing works. Right. Right, so the way this works is we just generate all the data, and then we fit both. We just fit the factor model to it, and we look at the factor score distributions. And basically, we say, are the factor scores multimodal? If they're multimodal, we'll say, wait a second, you really have classes in your manifest variables. If they're not multimodal, we say, hey, you have a factor model. Right, and as it turns out, and then the way we compare this, which the reason I'll go through this a little bit because I use this measure a lot. So we just use what's called the adjusted rand index, which is actually a measure Larry published in '85. Right, and what it does is it just allows us to compare a recovered partition with a true partition. Right, so we generate the data from a class structure. If I were to fit a latent profile model, I could compare like how well did I recover those actual class assignments. And I just compute this index, and it's bounded above by 1. Right, and below, it's unclear what the bound is, and it has an expected value of 0. So 0 basically means it's random. Who knows? Like we just did a terrible job at recovering class structure. Right, and then a 1 means we did a perfect job. Right, and so that's this big idea. And then we can see these are the factors that kind of in order of importance that kind of influence how easily we can detect a group structure. Right, so the type of overlap. So it's much easier to detect group structure if we have that marginal overlap versus the joint overlap, which makes, it would be worrisome if we found a different result, right? It'd be like, hey, wait a second. Everything I've learned is wrong. It's also easier to detect group overlap if we have, or to detect class structure if we have normal distributions, if we have normal clusters. It's the hardest situation is to detect class structure if you have uniform clusters, some kind of box. It's the easiest to fool it between class structure and non-class structure. And then obviously the probability of overlap influences, like how much they overlap influences how well we can do it. And then the number of classes is easier to detect exactly like 2 classes than it is exactly 6 classes. Right, and then the sample size basically has not much of an effect at all. And these are eta, you can think about these are eta squared, so it's like variance accounted for. So most of the variance accounted for is by the first 2 factors. But really the first one, just how they're overlapping in joint multivariate space. Right? In terms of a decision rule, this is just kind of the rule that we give. It's basically just an automated way to count the number of modes in the distribution. We just slide along the plot and we say, hey, okay, we're at a mode, and if we don't go back up again, we only had 1 mode. Right? So you just go up, you go down, and then you count to see if you go up again. Right? But the details are irrelevant, so we can ignore that. So the important thing is this. So this is, all of these were generated from a latent class structure. Right? So then we could choose, like, are we going to say it was continuous, or are we going to say it was actually discrete? Right? The real answer is they're always discrete. But let's say they're overlapping 50%. Like, what does having clusters that overlap 50% mean? Are they really clusters? Like, what if they overlap 99%? Like, when does the decision, which is an interesting question in terms of the field of cluster analysis, I still don't have a handle on when do 2 clusters overlap enough where they're not clusters anymore. And they're just the same distribution. No matter how you generate it. A lot of times people are like, well, it depends on how you generate it. It's like, well, for practical purposes, if they overlap, I mean, what about 99.99%? Like, when's the overlap enough where we can say they're the same thing? So if we classify something as continuous, then our recovery is really, really poor. So in that case, it would err to the error that, like, Rod was saying to make. So even though we know even though it could be discrete, it's such a poor recovery that it's much less of a problem to say it's really continuous. Because if we were to pretend that we knew it was discrete, we couldn't really get the true classes back anyway. It would just be kind of a fool's errand. We'd just be making up classes. Versus if we say it's discrete, we get a much higher level of recovery. Right? And then there's a big difference between these guys in terms of, like, Cohen's D, for instance. Right? And this is the question I mentioned. It's like, when do clusters, and I spelled do wrong, so that's maybe I shouldn't have pointed out. I should just hit the down button. My personal loathing prevented me overlooking it. So then we could also, this is just kind of summarizing what I already said. I just want to make sure that I get to everything, because I get so excited. I always have way more to talk about than I actually have time to get to. So I summarize all that in the ANOVA table, though. We can also go the other way. If we were to think about banning the ARIs, like what's our type 1 error if we say this is really good recovery? So if we're in a situation where we have perfect recovery, or what would be considered excellent recovery, we only make the mistake of calling it a continuous latent structure 3% of the time. So it's like a type 1 error rate of 0.03. We hypothesize that this is, like, we only make the incorrect assumption 3% of the time. As it moves down, if we use this 0.65 as our cutoff, which there's some theoretical reasons to think that this is a good cutoff for, like, what's considered reasonable recovery, then the type 1 error rate is 0.06, which is really close to 0.05. If we lower ARI, then the type 1 error rate just starts to shoot up, where we just don't know. Like, we make the mistake a lot of the time. Right? So it's really good. It's a good test to find truly structure that exists in your data. Right? If the structure becomes more overlapping, then this test maybe won't reveal it as well. But in that case, then you really couldn't classify people as well either. So it's kind of like, what are you missing out on? If we think about it the other way, what if we generated latent factor conditions? So how well do we get multimodal factor score distributions if it's really continuous, right? Do we get the other type of error? Right, so we can do the same thing. We can look at the number of factors, anywhere from a 1-factor structure to a 5-factor structure. And we did this, we increased the number of observations here to help improve our convergence. And then we did the full cross design again, just like before. And then we looked at all these data sets. And it turns out of the 3,500 data sets or so that we generated, we correctly got it right 95% of the time. So it's almost exactly a 0.05% error rate. It's a 0.06, which is good. I mean, it's really good for pretty good for a diagnostic procedure. The reason, and it even becomes better when you realize why it was making some mistakes, because this isn't a person looking at the distribution. This is an automated procedure, so we could do simulations. The reason it makes incorrect conclusions is because it's counting this as a little mode. Right? So I would argue that a reasonable person probably shouldn't be looking at the tails and saying, hey, that's a little cluster down here with a factor score of 3.5, like on a normal distribution. That's probably not the case. This is probably just having, either it's a function of the smoothing program that we use to smooth this, or it's just maybe not a large enough sample size to smooth out the little bumps. And so an automated procedure kind of went through the process. I think if you were to do it like as an analyst, you probably would not conclude, you wouldn't conclude that this has enough power. And if you did, I mean, you could investigate and see if there's something really weird going on up there, but probably not. Right, so that's kind of the general first step approach. I don't have a clock on my phone. Maybe I don't have my phone. I don't know. Just tell me when I'm running out of time. I was looking for a clock, but I don't see any of you. So it's a perfect classroom because it can make the students will feel trapped in here. They'll be like, "What is this guy going to shut up?" They'll look for a clock. There's no clock. Okay. So another problem is related to the. I don't know why I started with a little long, but related to, for this part of the talk, I'll focus on k-means clustering, which is just it's like a non-parametric version of latent profile analysis. You can think of it like that, where you're just extracting the means. You don't care about the covariance structure. For a lot of reasons, the covariance, people put too much emphasis on the covariance structure in the context of cluster analysis because there's a lot of room for overfitting the covariance structure. So covariance structures can cause a lot of trouble when you're trying to extract groups. So at the same time, we can think about if you have all these data together, so you have, in the cluster analysis literature, you have a bunch of, you could have continuous variables and you could have variables that have cluster structure. A lot of times the continuous variables are called masking variables because if you include them in the data analysis, they'll mask the cluster structure. So it's hard, it's almost think about like putting like smoke or fog over the cluster structure. You just can't see it there because there's a bunch of noise within the data. So if you throw all those into the analysis, you'll never see it. So what we're going to talk about here is what if we have subsets of variables that each define different cluster structures. So instead of saying all variables have to have the same cluster structure, what if we said it's possible that this subset of variables just describes maybe 2 cluster solution, but if I look at the next 4 variables, maybe it's a 3 cluster solution and so forth. And so I'll talk about the method and then I'll go through what I think is a very interesting example where this actually happens, right? So, but to talk about this, I'll just introduce what we're doing ahead of time. So this is just a scaling procedure. So one thing, and you can ignore the equations and just listen to me if you want. So one thing that people get wrong a lot is they do z-score transformations of all their data. Which is okay to do in some statistics. If you want to do regression, be my guest, do the standardized regression. If you're doing a cluster analysis, it's a terrible thing to do because the z-scores will actually cause the clusters to overlap more in the space. So what we do here is we do a different type of transformation that we've developed that actually highlights the cluster structure that might exist on a variable. So what this does is it basically says you can imagine what's the maximal variance for a variable. If you knew the minimum value and the maximal variance would be if half your points worth of minimum, half your points worth of maximum. That'd give you maximal variance. So that's like the most ideal cluster structure in the world. If I have this variable that says, oh yeah, 50% people here, 50% are here. This is the perfect world, right? So what we do is we basically compare each variable to its maximal variance. It's basically a ratio of an observed variance to the variance. In this case, we chose the uniform distribution because the uniform distribution is like the ninja of all sneaky distributions to cause trouble. It just sneaks in there and then it messes up the whole results. Right, so we do this comparison. Here's kind of a result of so this would be if I add random noise to my data. Right, so I start off at 0, so there's some kind of true cluster structure here. In this example, we use the classic iris data set from Fisher where he classified 150 flowers into 3 groups, right? So if you just classify the original data, then you get your recovery index is about 0.73, right? If you do this transformation, right, so here's our proposed transformation, then we can increase it to about 0.89. Which is very close to the same thing if you knew the groups ahead of time. This is what you see, always misclassify 3 flowers. Like nobody's ever gets perfect, right? And then if I add masking variables, this shows how much each additional masking variable degrades the original solution. So if I add 1 masking variable to the original data set of just standard normal noise, it drops off from 0.73 to below 0.2. So it's terrible. But the z-scores are the same. The z-scores do nothing to help the problem. Even if I don't add masking variables, the z-scores actually make it worse. You go from here, and then if I say, somebody said I should always do z-scores, you actually are doing worse than if you would have just left the data alone. Right? So you shouldn't live by some kind of mantra where it's always do z-scores. Right? This is if you standardize by the range, which is kind of been recommended since the late 80s. So here we're getting we can add up to about 16 variables of noise. So you can have 4 times as much noise as you do true variables, and you can still have them all in the analysis and still extract the cluster structure. I mean, obviously it gets worse as you go on, but it's a slower decline. It's like a gradual decline into death instead of this kind of thing, right? Okay. So then we can say, well, how many, now let's go through this. This is just, here, we can stick with this slide, right? So, almost done. The point of this is to say, if we could say, what's the worst situation that we could have, right? We could have a normal distribution, and what if we accidentally cut it in half, right? So we have no clusters, but we pretend like there is, right? We could cut it in half, and we could look at the ratio of sum of squares within to sum of squares total, for instance, as a measure, just like ANOVA, right? When you're doing ANOVA, you're trying to minimize sum of squares within, maximize sum of squares between, right? And then you get a big F-test. Cluster analysis is the same thing, but you get to pretend like you get to maximize the F-test. So you're not, cluster analysis is like ANOVA without random group assignment, right? You can just assign the groups to be the best ANOVA possible, right? That's what we're trying to do. We're trying to minimize sum of squares within and pull the clusters as far apart as possible, right? So if we were to make that mistake, if we really have a normal distribution and we cut it in half, then we have, this is what that ratio would be, for instance, under a normal distribution. So if we, in decimal terms, it'd be 0.36. Right, so if I do a cluster analysis and if I take a data set and I cluster it into 2 clusters and I calculate the ratio of sum of squares within to sum of squares total, if that ratio is bigger than 0.36, then I can't be confident that I'm not just chopping up a normal distribution. If it's less than 0.36, then I can say, yes, I have some kind of cluster structure, let's proceed. Right, so it's kind of an initial, like, let's get the hall pass from the monitor, and then we can go on and keep doing cluster analysis, right? If I don't get it, then I'm like, well, I don't really know. And I'm naturally conservative, so I don't want to just, like I said, don't want to impose cluster structure where it doesn't exist, right? And then we could work out a way to test the number of clusters and so forth. And we see that it works. Like, this is the iris data. If I do my initial 2 cluster solution, I get a ratio of 0.22, so it's below 0.36. So I say, let's proceed. And then I have this other ratio. If I minimize it, it tells me how many groups. So in this case, it tells me there's 3 groups. So it works really well. There's a test for how well it works. Like here, so this is the kind of the prior gold standard for choosing the number of clusters, and this is kind of our proposed method. So you see that for each column, there were 90 data sets. So if it was 2 clusters, then we always get it right. And then it's 3, like we tend to underestimate and say there's 2 instead of 3. So we kind of, up until 6, we underestimate, and then over here we kind of tend to overestimate. But it gets really hard to extract 7 to 10 clusters, right? But here it's just, it's much better than what people have currently been doing. And they're both based on different functions of sum of squares within and sum of squares between. Right, so we're kind of moving forward to this. And then we say, well, how do we want to select the groups, the clusters that go together? So what we do is we just take our data set and we say, okay, let's do a k-means cluster analysis, but I want to do it a variable at a time. So I'm going to cluster analyze the first variable, then I'm going to cluster analyze the second variable, then I'm going to see how close those 2 solutions of those variables correspond. And if they meet some threshold, I'll put them in the same subset and say, yeah, this is kind of describing the same cluster structure. If they're random, if they correspond 0, then I say, wait a second, it doesn't make a lot of sense for the most part to put these together. And we build up beyond just single variable to time comparisons. We do pairs and triples and so forth to make sure that we're not missing some structure that can only emerge in a certain multivariate space, right? But we start off at a single variable partition at a time. We keep going through this iteration. We do this process, we do this classification and so forth. And we just repeat it until no more variables can be added to the set of variables, right? And then we set that set aside, and we go back to our original variables and we do the process again. And we just keep, and every time we extract a subset, we just set it aside until we can no longer put variables together. And those variables are just continuous. Those would be left to the factor analysis or something like that. Right? And the way this works, so here's an example. So I did a simulation and we show it works, but I want to make sure I get to the example, which is more interesting. Right, so we have 1,818 college students and their internet usage, right? So we ask them, what are you doing on the internet? And there's these options, right? So you either can be reading and writing email, instant messaging, you read the news or other kind of fact-based content, online shopping, you can buy and sell at eBay, which is actually very popular, apparently among undergraduates. You can download music, gambling, there's a contingent of undergraduates, at least at the University of Missouri, are big into online gambling. There's even a smaller contingency that sell and trade their own stock, which I would have never guessed. Undergrads, and then there's a larger contingency that are viewing and downloading sexual material, like pornography, or they can either spend time in a sex chat room or a non-sex chat room. Or you can play games, like just non-betting games, like World of Warcraft or things like that, Farmville or whatever the popular game of the time is. Or you can research course-related material, or you could read or review artistic content. A lot of times that'd be like maybe reading fiction or something, or like you have a favorite author that's just published in the internet. And then in this case, we just have, these are 14 items. They were measured on an 8-point Likert scale. Okay? So we go through this process, and we look for 2 to 6 clusters through this kind of iterative process, and we come up with 3 different subsets of variables. Right, so we have and then we've named them a general usage subset. So we have a subset of variables that defines a cluster structure, where these variables are reading and writing email, instant messaging, reading news, downloading music, buying and selling stock. This is like everybody either does or doesn't do this, basically. And then we have a gaming subset, where you either spend time in non-sex chat rooms. It turns out if you are in a chat room, it isn't talking about like sexually related activities, then it's usually around some kind of game, like people talking about like, this is my strategy, like how I do these raids and stuff. And it's beyond, like I'm a little, just barely older than the cohort, like my brother's cohort, like they're playing all these online games. Right, then you could also play non-betting games. You're just playing games, maybe playing games on your iPhone or so forth. And then there's this more sensational, and I always think about this as the stuff you wouldn't want like your grandmother knowing that you're doing when you're like in your free time. So you're just like rampantly buying and selling stuff on auction sites, you're gambling your tuition money, you're viewing and downloading pornography, and you're spending time in sex rooms, and you're actually reading fiction actually slipped into this category, right? And reading's becoming a dead art, apparently, which is amazing. Like apparently not. Yeah. And then the 2 variables that didn't map on anything were whether you buy things online and whether you research course material, which is nice because it makes sense, because all students should be doing some research, and a lot of people now are using Amazon and things just to buy stuff. Like they don't do as much. But if we break this down, so then we can look at the agreement between each of these, or the overlapping cluster structure. And this is the adjusted rand index, but it's just, you can think of it like a correlation in this context. You can almost think about these clusters as being orthogonal to each other. If I told you where somebody was located in the general usage cluster, you basically have no information about where they're in the other 2 cluster structures, right? So these are independent chunks of cluster information, right? And it's very nice. They're just not related. This is basically all just 0, right? And then the way this breaks out is like this, where you have, and these are standardized values, right? So this is just the standard deviations below the sample mean in the clusters. So this is for the general usage category. You basically just had 2 groups of people. You had low usage and high usage. So people who did these things a lot and people who didn't do them as much, right? And the biggest differentiator was instant messaging. So people who do a lot of instant messaging, or maybe not so much. But you also had separation like on maybe email and reading news and stuff like that. Students are emailing less and less and doing more Facebook message. They tried to get me to set up like a Facebook account for my class so I could contact my students. I was like, that's just weird. I do that. And then same thing with online gambling. Here you get 3 clusters. You get a cluster of basically people who don't do it, either one. But then you get this cluster where people like to play the games, but they don't really want to sit around chatting about the games. They're just in it for the gaming experience, then they're done. And then you get the more immersed gamers who they play the game. They're more, in terms like so I did this work with some clinical psychologists, and there's follow-up surveys. Like they're just more immersed and almost more obsessed with the game itself. Like the game takes over their life. And at the University of Missouri, there was a concern for a while. There's a lot of freshmen that were not making it to their sophomore year because of this situation. And then here we see that here's the splits too percentage-wise. So 36% of the people were in this low usage, but most people are in the high usage, just general internet usage, 64%. Versus here the low gaming was the 19%. And then you still had you had just moderate, people playing games and stuff like this. This is a few years ago. I'd imagine this category is bigger because just for handheld devices are more popular in apps, and there's everybody's playing a little game, it seems like. But what the clinical psychologists were most interested about was this 3rd group of variables, this more sensational group of variables. And then here we had 4 different groups. We had a group that was almost primarily defined by the only thing they really did in this category was read fiction. They just read a lot. Right? So that's kind of what drove them. Then you had this kind of, and I can't remember what the acronym stands for, I apologize. It's high something. I don't remember what it is. But they do everything. They just basically, if it exists on the internet, they're doing it. So they're 6 standard deviations above on chatting in sex rooms. They're like 6 standard deviations above on gambling, 3.5 they're auctioning stuff. So there's a lot of students that try to use eBay as like an income source, where they buy stuff and they try to resell it, and they buy it and resell it. And I guess that's maybe it's to fund the gambling. But the interesting thing is that's only 1% of the total population, which from a conventional, if we do all these variables together, we find this structure, right? These 5 variables drive the entire results if all the variables are included in the analysis simultaneously. So you'll get a 2-cluster solution with low and high usage, basically, and with no real discernible pattern down here. So from a clinical psychology point of view, they were very excited because then you can target kind of these people in terms of intervention, maybe retention in terms of keeping them in college. Then you have the group of people who don't really do anything, and then you just have the group of people who view pornography, right? So they're not really comfortable chatting, and they're not into gambling. They just want to be left alone, look at their pornography, right? That's all. And that's 2 standard deviations above. Right? So it's interesting in that, and then a lot of the criticism is like, well, does this really tell you something you'd get if you just were to do a factor analysis? And the answer is the fact. Yes, go ahead, please.
So why do the readers fit in with the sensational group? Because they're not doing anything.
I think it's because the reading variable got pulled in with this group. So this group had a higher instance of reading also, so they pulled the variable in. Right, but they pulled it into the mix. I think you would not lose anything, like if I were to do this in terms of, so in this case it's just a demonstration of this is what the algorithm gives. If I were to like think of it more from a theoretical, like clinical psychology perspective, I would say we could safely remove this variable from this group and you're not going to lose any information, and you go to a 3-cluster solution. Right, because, and then the interesting thing about this high usage group is not that they also read more fiction. Right, it's probably more erotic fiction. It's probably more erotic fiction. Kind of like what was mentioned earlier. But yeah, that's a potential drawback of the process, is it can have like this, yeah.
How do you differentiate that from just a multivariate outlier? Like if these things just happen to go together, it's a very small representation. It's phenomenally huge.
I think that, I think that's a good question. I think there's 2 things. I think it's hard to find, in some sense it's hard to know what differentiates, like, that's another question, like how far apart do clusters have to be? Like how many outliers have to be together before it's a cluster? I don't know the answer to that. But it's also, in this case, it's hard to identify because it's only an outlier in this. So if you think about this as a 14-dimensional space, it's only an outlier in a 5-dimensional, or 5-dimensional subset of this space, because 2 variables aren't included on here. Right, so in the 14-dimensional space, there's a 5-dimensional subspace where they are those 25 people are outliers. But if you look at the full 14-dimensional space, you wouldn't detect them as outliers because they're also in the core of all these other variables. They're not differentiated on these variables. So they'd be in the core, the meat of everything else. So they might have a slightly elevated score on like a standard, like multivariate, like outlier index, but it's not gonna be like, oh, this is a huge outlier, because the majority of the full space, they're not outliers. Right, if you were to slice it, if you were to take the other 9 dimensions, they could be right in the middle of the distribution. Right, so the multivariate outlier is kind of assessing your outlierness across all dimensions simultaneously. Right, does that make sense? It kind of pulls you back in.
Yes.
Right, so if you want, you could think about this like this. You're also just dividing up the subspaces to find outliers within subspaces. In this case, it just happened they were high on everything. But I could imagine another maybe application where you might be high and low on some different things where it's harder to detect. But if you were to do a factor analysis, then this is how the variables load on the factor analysis, where you get the letters correspond. The original blocks are what we found in the prior slide, and then the letters now correspond to what they would be in a factor model. So in the factor model, you'd have one factor that, for instance, was email, instant messaging, and downloading music. Then you'd have another factor that was reading news and reading fiction or researching. So you have it from a variable perspective. You also have a highly interpretable solution where it's more driven by the content of the variables versus like the behavior of the people, right? And you wouldn't but you don't pick that behavior up in terms of the factor scores, because the factor, like I said before, the factor distributions pull everybody back to the middle. So the factor distributions are trying to homogenize everybody into these normal distributions, right? And then you'd have a factor for non-sex chatting, auction, gambling, and sex chatting, and then you would have a playing games, downloading music, viewing erotica factor, right? And I guess online shopping gets thrown in with gambling and chatting. Right, so in some ways, there's like, it makes sense, but maybe it's not quite as clean of a solution. Right? So you can have, in this case, you could have, cluster structures and continuous structures living together. But in this case, you could have multiple cluster structures and continuous structures living together. And if you treat everything as the same thing, you never see any of it, right? So you miss out on the richness of the data, just like approaching it with a sledgehammer or whatever, however you want to think about it. How much more time do I?
It's about 10 to 1.
That's right? 15 minutes is what Carolyn told me?
It goes to 1:30.
I can keep talking if people want more.
I bet you people have questions. So.
I can answer questions, or I can 15 more slides. So whatever you prefer.
Let's keep going.
Okay. So then we switch gears a little bit to this more general problem, is kind of a big data issue. As we've been talking about, everybody, is like this very vague term that nobody knows how to define what big data really is. Right now, I'm thinking about it in terms of just a lot of variability, high dimensionality. And what we have with a high dimensionality is we have a lot of problems. We have interpretation in a high dimensionality can be very difficult. It's usually, a lot of times people do principal components analysis and factor analysis because you feel like it's easy to interpret what you have in kind of that reduced subspace. Computation, for instance, is a big problem in a high dimensional space, especially if you move to more likelihood-based computation approaches, like the EM algorithm kind of breaks down in a high dimensional space. But even traditional, like k-means clustering and things like that, if you get a high enough dimensionality, you can have difficulties. And then practicality, as the number of variables increase, the likelihood of all of them contributing to a coherent cluster structure decreases. Right? You're more likely to get these noisy variables and so forth. Right, so what we said is, well, data reduction can address many of these problems, but we might want to do a type of data reduction that preserves the cluster structure specifically. Right, so we know in factor analysis, it doesn't matter what we start with, it tries to funnel it all to a normal distribution. Well, now we want to say, if we start with clusters separated up here, we want to funnel it to a latent data space where they're still separated. Right, so if one's over here up in here, we shoot it from like 2 dimensions to 1 dimension, we still want them to be separated. We don't want to intermix them in a normal distribution. So the way we're going to do here is traditionally what has been done was something called Tandem Analysis. And I came across this problem, actually. I left here and then I was reading some chapter Larry had in like a 88 proceedings of like a German classification society or something, where Hans Bach was the editor, and it mentioned this tandem analysis. Like, hey, what's this? Sounds interesting. So it mentions it, and it's interesting. And then there was 3 paragraphs talking about how bad it was, and then I was like, it's never to do this thing. And then I was like, well, I had to think about it a little bit, and then it makes sense why you don't want to do this, right? So what people traditionally do is they do a principal components analysis or a factor analysis. It doesn't matter which one, and then you keep your factor scores or your component scores. So you keep them and set them aside, and then you want to cluster analyze those factor scores or component scores and see what's going on, right? So the reason this is a silly idea is because if these were my 2 clusters, like I have a blue cluster and a green cluster, then my first principal component would go right between them in this direction, right? So that'd be the direction of greatest variation. And my second principal component then, because it has to be orthogonal, would go this way, right? In this case, if I'm doing data reduction, I would only extract 1 principal component. If I did that, then that means all the blue dots would get projected onto this side and all the green dots to this side, but in the same spot. They'd be intermixed, right? So you can no longer separate clusters in the principal component space because by the projection, I intermix them. If for some reason I were to keep this one, then I could get the blue dots over here and the green dots over here, and it'd be perfectly separated, right? So then we thought, well, how can we come up with a way to create a new index where we could choose a projection that looks like this, where it keeps everything separated? So that's kind of the general goal, right? So this is how we do it. But in words, what this is doing is it's taking that same index before, where it's trying to maximize the clusterability of a given variable, which means that if it were a perfect situation, half your points would be here, half your points would be here. If you had 3 clusters, you would have a third here, and a third in the middle, right? So you're basically trying to spread your points out evenly across the entire latent space, if you can, if there's really a cluster structure, right? So this is the index we're going to maximize, and we just use all the same rules of principal components. We're going to make sure, in this case, we're going to make sure the length of the coefficient vectors will be 1, just like an eigenvector, and we'll also make sure that they're orthogonal. So when we do the projection, they will be at right angles to each other, right? And the problem is principal components has a very nice decomposition of the covariance matrix. It's just like, hey, it's your eigenvalue eigenvector structure. Here's your factor loadings. In this case, it doesn't work like that because we're trying to look for this crazy thing here. So what we do is we just take a sphere in whatever space we're in so we take a hypersphere in the p-dimensional space, and we just find a point on that sphere that defines our first coefficient, and we just basically use a search algorithm to move along the surface of the sphere as we maximize this index. So you can think about each point on the sphere corresponds to a value of this, and then we hit the highest value, we stop. And then there's like some little twiddles where we can jump around and things like that to make sure that we're trying to really find the highest value. But the way it works, and then here's the algorithm, which is less of interest for you. But if I did this and anybody wants the slides, I'll forward you the slides and you can read through the process. Right? So then we say, well, how many projections should we extract, right? So this is the kind of the perennial problem in all this is like, how many clusters do we need? How many projections do we need? It turns out that the one of the kind of best approaches in factor analysis has been the Horn's procedure, or the parallel analysis, depending on which software you use and what it's called, where you basically are comparing the scree plot of your eigenvalues against the scree plot from random data that are uncorrelated. Right? Same thing here, only we use the uniform distribution. So we basically take our data set and we generate random data from a box with our data set that fits perfectly inside. So if it's in 3-dimensional space, we just figure out the bounds of our data, and then we just basically take a 3-dimensional box and we generate random data from that, and then we do the same analysis on the random data. And we basically say, if I can get this type of profile for this index from random data, then if I don't beat the random data, then I don't want to trust it, is the basic idea. And what it looks like is something like this, and I'll go back to the slide. So this is for the iris data, right? So this is our random data, is the circles, and the iris data is the squares, right? So and I'm extracting these principal axes of principal clusters. And so if I do the first two, I got an index of, like, the first one has index almost 1.4, and then a little bit less than 1.2, but then I have this crossover point around 0.9, where now I'm saying random data is outperforming my analysis on the iris data. So I would stop here, and I would only keep 2 cluster projections, right? And then you could go back and you can interpret the same way. So I would ignore these 2. Right, and I could interpret these the same way as I would a factor scores or factor loadings, right? So then this is saying that the cluster structure on the first dimension is mostly driven by petal width and petal length, right? But mainly petal width. Versus the second dimension is more of a contrast between petal length and maybe the sum of sepal length and petal width. But those 2 dimensions themselves really define the cluster structure. Then if we were to plot these 2 guys, then it looks like this, right? So we have, this is in the reduced space. So we have one species of iris here, then one here and one here, and then we see, once again, we'll still misclassify the 3 points, because you always misclassify the 3 points, and they're right here. Right, but we go from a 4-dimensional space to a 2-dimensional space, which is really cool, right? But even cooler is this next data set, is this crab data set. Because this has 4 clusters, and nobody's ever been able to really extract the 4 clusters, whether you analyze the 4 data set or look at subsets of variables. Right, so this is on the diagonal. There's male and female crabs, and there's like a blue species and an orange species, and it's a data set that's available like in all the Agreste's categorical data analysis book. So there's 5 different variables, and then on the diagonal is the univariate distribution, and then on the off diagonal you see the bivariate plots, and you see, like here, you see a little bit of separation, right? And you see it here, and you see maybe a little bit of fanning here, and that's mainly the male crabs and the female crabs being separated from each other on these bivariate. But you never see the 4 clusters. If we use our procedure, then it plots out exactly like this, where you get a cluster species in each corner of a 2-dimensional space, and you just get a little bit of overlap right here, and then a little bit of overlap right here. Right? If we compare it to other methods, if I go back to here, we compare it to if, so here's our proposed method in the recovery. So for the iris data, this is just as good as discriminant analysis if you were to know the groups ahead of time. For the crab data, almost everything else is equivalent to random, any other procedure that you can do to try to do the clustering, versus this is a really good recovery. But we also show when it fails, which I also think is important to show, like, hey, like, it's unbelievable when people present something and they try to claim it works all the time, because this doesn't. So this is a data set with which I don't know why anybody would do this, but I found this data set where they basically had a bunch of different types of glass, and people like beat it with a hammer and mixed it all in a bag, and then asked if you could classify like which fragment of glass came from which initial thing. And no, like I can't, right? But the good thing is like I can do a little bit better than the other best, right? But it's still terrible, right? And they can do the same thing with simulated data, right? This was like highly overlapping in this was like for a reviewer, and we did some simulated data, but we see like we could project it down into 4 separate spots. And that's all I have. Like that's like kind of thing. It's like that's kind of the kind of notions of like what is cluster structure and how do we preserve it in these like layers and hierarchies of dimensionality that we think about, and how it's important. Like, you shouldn't always assume something is cluster structure or isn't. You should actually do some kind of diagnostics to figure out what's going on. But otherwise, now I can answer questions.
Okay, data therapy questions?
I need a data therapy. I should open a data therapy center. I like that. Yeah.
But it's really kind of a selfish question
Okay.
that I struggle with. And so I've been doing a lot more with kind of time series data and lots of mean person variation.
Right.
And I think we've got a lot of really cool stuff coming out of like kids Penn State with kids Illinois.
Yeah.
And really have like it's just kind of a different kind of measurement. It's like we're talking about typology.
Right.
Right. And even if you take something like the Big Five versus
Right,
the
right.
most replicated
Right.
factor structure out there for cycle variables. If you do it on individuals,
Right.
measure lots of times,
Right.
you don't get those
Right,
factors. Right. So are people doing this type of stuff, with thinking about that within person component as being somewhat different than this kind of between person kind of like for most part you're talking about these
Right.
types of people.
Right. Yeah, I think that's so you're actually like looking at clusters within people. So you would.
I'm asking the question: do they exist?
I haven't seen anything like that. There is, like you mentioned, like Peter Molinar, there are people doing a lot of like looking for different trajectories or typologies across time, but that's still classifying people into different groups. So this type of person, like, oh yeah, this is somebody who drinks all the time. This is somebody who maybe started college not drinking, but now they drink all the time. But it's still not looking for differential, like signals within a person. I haven't seen it. I think that I don't know. I think that's a really interesting perspective. Then you could classify. I've talked a little bit with a clinical psychologist in our department who's doing the EMA data, where they carry around the phone and do mood responses. Who wants to classify mood patterns in the day, and then see like it's for a manic depressive and also bipolar people to see which state they're in, to try to classify them in a particular state to see if they need like different prompts or something to help them like adapt to their state. But that's the closest thing I've seen. There's not a lot of comparatively, there's just not as much even time series clustering as there is cross-sectional clustering. But I think it's becoming more and more and more. Yeah.
Still trying to decide if I believe in clusters.
Well, that's fine.
I guess, could you go back to your
Internet example?
electronic data, yeah, your online data.
Yeah.
So, if you plot those out, you get real separations between people that are in the clusters and out. Like, how do you what's the diagnosis like here on how much those clusters separate out? Right, so in the general usage at high and low general usage.
Right. The 1% cluster is very separated, like way off in the corner. So if you were to think of, even though it's in 5-dimensional space, you could think about like that high usage cluster will be out here, like by itself, because it's high on everything, and it's just. But like was brought up, it's only 25 people, so that might be a problem. And then this cluster is pretty well separated, like down here, because it's a low usage. But these two clusters are less well separated, right? But so they just kind of in 2-dimensional space, you might have like a little. If I were to maybe like a little cluster here and like a little cluster here, it probably more overlapping than that. I mean, it's really probably looks something like this, right? So you have less separation among the three, big separation here, but you still have enough to say this. I mean, they're different, but they're going to be more overlapping.
So you got really different things when you did the factor analysis.
Right.
And really different how to structure the data. And so how do you? So when you did your factor analysis, I take it you had multimodal.
Well, in that case, there's not.
Like, how do you adjudicate between which way to look at the data when you have such different?
Yeah, I mean that's hard. I mean, part of it's the question. Yeah, part of it's the question you want to answer. But for me, I think the driving thing is like, what's the goal of the question? And so, if the goal is to talk about how variables are related and which things go together, then it seems like factor analysis is probably the more appropriate thing. But you have to be careful. The caveat is, even though you're doing that, you have to be very careful then to talk about people in the factor analysis, because you have to be very, like what we talked about, you have to make sure the factor analysis is appropriate for that. If your goal is to find maybe at-risk individuals, especially like in a clinical psychology setting, then maybe like searching through them through cluster analysis can be very beneficial, because it'll find things that would not be identified. Like these groups just not identified in the factor model. And mainly it's because the factor model doesn't group the variables the same to identify them, and then the driving thing that's driving the variance is really this bigger split separation. Right, so if we think about a 50-50 split has the biggest variance, then this factor will have, if we were to fix a loading and free the variances, then this factor, if these were the factor loadings, this factor will have the biggest variance. Right, and then there'll be this factor, and then this factor will have the smallest variance.
But that's kind of a dangerous approach, right? I mean, I'm thinking about reading and reading disabilities.
Right.
So, I mean, there's a bit of a debate about whether dyslexia, for example, is really a thing. Or
Right.
whether there are just a whole set of skills, reading skills, that
Right.
are all in a normal distribution. There's really something. And I mean, I just, not knowing this, and I'm going by my fingernails.
No.
I find that I find that discussion troubling and interesting, and I'm not, the more I read, I'm not really sure I believe in dyslexia.
Yeah.
And so where does theory come in? I mean, because
Well,
with factor analysis, you can do a confirmatory.
if I had my pick, I would say do a confirmatory factor analysis first. Like always do, if you can do something confirmatory first. There just isn't confirmatory cluster analysis really.
That's my question.
Right, so this would be, I would say this approach is more on par with exploratory factor analysis. If you have a strong theory, then I would almost always, just like I think when I took it from Rod, I would just almost always advocate testing the model that you believe in.
So what are the barriers to making this, to reworking this as a confirmatory approach?
It'd be hard because you have to, so in factor analysis, to do a confirmatory approach, you have to have an idea of your underlying factors and which variables belong to which factors. For cluster analysis, you'd have to have an idea of like how many clusters exist, but then which people belong to which clusters. So there's a lot more things there's a lot more mistakes to be made, perhaps, because if you have, let's say you have 1,000 people and 10 variables. In confirmatory factor analysis, you're just trying to specify 10 relationships. And if you were doing confirmatory cluster analysis, you'd be trying to specify 1,000 relationships at a time, because you need one for every person. Right? So you could try to maybe do, maybe the closest would be an in-between, which we're starting to do a little work on specifying the size of clusters that we think ahead of time. So we don't know who belongs to it, but we might think that there's a 1% cluster out there. So we'll do, it's like a constrained clustering. We'll say we're going to do the cluster analysis, but we're never going to let it grow, bound how big and small it can be. And so if it's really a group of at-risk people, we wouldn't expect it to be more than 3% of the population, for instance. And then, so we could put like little bounds and see, and then do some testing. But it's a lot more the statistical underpinnings of a lot of cluster analysis isn't as rich maybe as what's under factor analysis, so you don't get the likelihood tests. And so confirmatory factor analysis works because it's like, you got the chi-square distribution and then boom, p-value. And the factor and cluster analysis doesn't really have that.
It's a real different situation to say that nature gives you clusters, which I get kind of species of Irish.
Right.
Because I mean, I can, and to say we're going to create clusters for clinical convenience, because then we have normal distributions and we take a tail or whatever.
I agree with that.
And we declare it an entity, which is fraught with problems.
Yeah, that's the whole DSM-5, right? That's the,
Right.
that's I think that is a problem. I mean, even just in the context of alcohol abuse, they have 11 items now, and they do a threshold at 2. 2 is like a moderate problem, 4 is like a problem, and 6, if you endorse 6, it's a severe problem. But it's just basically an IRT scale that they're putting. I don't think they know what they're. I mean, that's just very strong. I don't know if they've thought about all the kind of implications in terms of statistically. They just had people in a room sitting around, I think it should be this, and there were experts, and this is what we think. But it's hard. I mean, from a clinical convenient, like if you're treating patients, though, you need, like a clinician needs some kind of maybe inventory or battery to help make a diagnosis. So I mean, there's definitely a trade-off, I think, in like how we think about these things. But I agree with you. I do tend to believe that we should err on the side of continuous data, like a factor space. But if we can extract things that are actually there, then maybe that's more interesting.
Is that mutually exclusive? I mean, can't you look at within that or within class variation? Right? So isn't like in mixtures, can't you have like a distribution around a given class mean?
Yeah, so you get a distribution, but it's still, the question is like, do you have multiple means or one mean? I guess that's the real question.
And where's the what are you trying to analyze? You're trying to is being kind of having a diagnosis or being high for that diagnosis versus low for that diagnosis.
Right.
Is that meaningful? But it's easy. You still can have variation. You look at both the mean and the variation. So
Right.
the class is taking care of the mean, and the variance around each respective mean
Right.
can still be meaningful.
Right.
So you kind of have the best of both worlds in terms of the variance and the mean structure.
Right. Yeah, you can look at both.
What are the size constraints?
None for like, so it depends on which type of clustering you're doing. If you're doing k-means clustering, you don't.
Yeah,
It's just a Euclidean distance, so you can do it any way you want.
because I think a lot of genetic conditions.
Right. Right.
And you kind of mentioned somebody with a condition itself and try to find the cluster genes associated.
Yeah, I think in those cases, I mean, I do think you can't even fit a factor model. Just, I mean, you have more variables than people, so you can't. So there's situations where one is not an option. So in that case, you want these really fast, kind of more computer sciencey driven clustering routines than you want statistical driven.
Seems like you could also use it on fMRI.
Yeah, we're combining some of this with network ties to try to figure out like how to extract network like globules of fMRI connections. So we're doing the network ties in combination with some of the clustering routines to say, oh, this area is activated or not, or so we're doing that. Like, so it's really cool. It's very cool.
I just wonder if our data set is big enough, and could we just discrete randomly into R and then do a cross validation?
Yes, that's kind of the last part of this that we're almost done with, that we're going to put in before we submit it. It's just is like having some kind of approach to use like a k-fold cross validation to help us decide like how many subsets there are, how many clusters there are, kind of like maximizing one of those replication indices. That's exactly right. That's exactly right. Do you have did you have a question?
Yeah, sort of.
Yeah.
Look out, Doug.
It's a curveball coming.
It kind of rolled off the non-conventional question. In psychology, there's been a long history of classing variables in terms of relative dimension.
Right.
And there's some very well-known papers on this too. And so I've often thought that this is kind of a bad approach to the whole thing, putting it in either.
Right.
And part of your presentation is on the either or level too.
Right.
And I'm thinking that you ought to really be able to present both analyses, and from either or analysis, either or and, you can provide some interesting information
Right.
to know about this structure. So
I think that's true. I think that the end goal would be like the part I've had. That's the end goal for me. I think is, but the part I'm having trouble with is what's the interlocking mechanism where you really can explain these results in a nice narrative with these results. And sometimes it's difficult. Like it's just very difficult to figure out how those interlock together.
That's where theory comes in.
Right. But I think that's true.
People make a lot of bad decisions. Like you see these like regression models with 50 predictors in them, and
Right.
we're looking at this stuff that they're in a multivariate space. These people don't exist.
Right.
Holding everything constant. So it's just this massive study of extrapolation.
Yeah, I think theory, I would say I welcome that, and I would just say people need to really pare down their variable set. Like if we need to, that was exactly my response. It's just we need to like limit it to a much smaller subset of variables. Even this, like 14 variables, yes, you probably could have done like better with. They probably could have done better with a more like a theoretical approach ahead of time. But I don't know. I mean, I don't mean to be critical, but it makes it hard. Like it's like the theory. It's hard not to make up the theory after the fact, right? So I think that that's where the cross validation comes in, which has definitely been an issue, like across most of all the psychology journals lately.
So what size n would you not cross-validate?
I don't know. I would try to cross-validate almost anything. Just if I'm weary of papers that are not have some kind of validation in them anymore, that aren't like just at some level. And I know that raises the standard for like a data collection and everything in terms of like what you'd expect to see in the more of the top tier journals. But at the same time, like there's so many like these after the fact studies that are showing like so many of these results can't be believed. It's like I find that's probably the most troublesome thing in psychology, social sciences right now is the.
Mostly social psychology.
Yeah, especially. I don't want to pick on social psychology, but it is mostly those journals right now.
Well, fMRI data has had.
Yeah, fMRI data. Yeah, you see the regressions with like 12
Social psychology.
12 people.
Well, that's another thing with in-person data. Like you can't replicate any one like fMRI that's between people within person.
Right.
So like, what are you saying if it doesn't exist in one person, but it's there in aggregate, but not within any individual when you follow them, over time?
Yeah.
Emerging structure.
Yeah, emergence.
Or lots of false positives.
Yes.
Or,
Yeah.
Yeah, it's all bootstrap. Isn't it the same data
I don't know. I mean, maybe. I mean, bootstrapping and cluster analysis is kind of weird because because even if you don't, like, I still think you have to have a big data set to do an effective bootstrapping and cluster analysis. Because if you do it on a small data set, then you can artificially create the clusters through the bootstrap, and then it'll think that you're getting these, like, if the sampling with replacement, it'll start piling up observations in a little mass point, and you think you have a cluster. So, but if you have a big data set, it works better. Like if you bootstrap down into like from a big one to maybe a set of smaller ones or something. But, yeah.
This is a straightforward question. I didn't look through your data well enough, but have you developed programs and graduate students who run this?
Yeah, most of them are in MATLAB, and we're starting to move some of them to R now, because R seems to be more popular now. At the time when I first started, it was kind of R was just coming out. Yeah. Yeah, so it's like started with Larry, and it's like, oh yeah, like MATLAB, and I was like, okay, I like it. And then now though, it's like gradually as the time goes on, it's everybody's doing R and it's free and people, and I see. So we're starting to move a lot of our stuff to R. But yeah, definitely, if anybody wants to, just send me an email, and I guarantee I have it in MATLAB, and I might have it in R.